All right, we're going to take a look at how we can use integration to find volumes. We looked at area, the area between two or more curves previously. Now we're going to move from two-dimensional objects to three-dimensional objects. So when we talk about volume of a solid body is just a solid three-dimensional object. In particular, let's talk about a right cylinder first of all. That's a solid body that has a constant cross-sectional area. And if it has a height of h, then the volume is simply that cross-sectional area times the height. So for example, an example of a right cylinder is a right circular cylinder. I'm going to try and draw a three-dimensional object on a two-dimensional sheet of paper. So the dashed line would be what we call a hidden line, right? And so here we have a right circular cylinder, and there are dimensions we can talk about. It's the base and the top are the same. It's a constant cross section in this case, and the circle's radius, let's call that r. R is the radius, and then the height of the can. So right circular cylinder can also be called a can, I guess, is h. And then, so what would the volume of this be? Well, the constant cross-sectional area A is the area of this circle. So what is that area equal to? Well, the area of any circle of radius r is what? Pi times that radius squared. And so we can find now the volume as just the product of that cross-sectional area times the height. So pi r squared h. Okay, so such an object, sometimes called a prism as well, doesn't have to have a circular constant cross-sectional area. It could be a square or a rectangle or a triangle or any other shape, as long as it's constant in area. Then the volume, the capacity, right, the amount, basically, how much, if this was a can, right, how much we can put inside, how much liquid could it hold, for instance, right? That's the volume, right? Three-dimensional objects, we can talk about their capacity or volume. So the thing that we want to look at, though, is what happens if this cross-sectional area is not constant. What if it's changing? For example, maybe I have an object that looks something more like this, right? Where at any point the cross-section may be circular, but as we move up, those circles are getting smaller and smaller and smaller, and we've got sort of this dome-shaped object. How in the world would we be able to find its volume? Because again, the cross-sectional area is not constant, right? If it's constant, we can then simply multiply that cross-sectional area times its height, but here it's changing. Well, so what we're going to do, we can set up this in such a way that our coordinate axes are maybe like this. This would be the y-axis here. And so if this is the x-axis, then notice this is when y is equal to what? 0. And let's suppose the height of this object is h. So at the very tip of this object here, right, then this is y equal h. That's the height of it. So how would we go about finding this volume? Well, we're going to think about doing this with respect to the y-axis the way I've got it set up here. In other words, I'm going to partition this y-axis from what? From 0 to h, right? If that's h is the height, from 0 to h, and I'm going to break it up into n equally spaced with equal width subdivisions, right? And so an arbitrary one maybe looks like this. Since each has the same width, we're going to call that width delta y, because I'm integrating with this is the y-axis. We're going to be integrating actually in this case with respect to the y-axis, and there's some arbitrary, you know, we can pick again some arbitrary point in this interval, some y sub I, if you will. It could be the either endpoint or the midpoint or whatever, and we can come over here and we can find, sort of come here and slice through this shape, and what we're going to do is we're going to cut out a strip that is with this width of delta y. We're going to cut out a strip of this dome, if you will. And so what would that strip sort of look like there if we come across here? Well, it's going to be, try and draw it here, and in the back we'll have some hidden lines. All right. So what is this thing? If let me take this piece out that we've cut through here, what's it going to look like? From the side, it's just going to have these curved pieces here from the curved side here and here, and from this direction, looking straight on, it looks like this. But if we take it and look at it from if we're looking at it from underneath it, turn it over, what's it going to look like? Since it's a circle, right? There's a circle cross section, and there's some thickness to it, so I'll sort of draw it like that, right? And the question is then, can we find this area as a function of y? Well, we could probably estimate it, right? If we know maybe what the function is that gives us these curves, we can potentially find out what the radius of this circle is, and then we can estimate then the area to be pi times that radius squared. If it's a circle. Even if it's something else, the question is, can you find this cross-sectional area? And it may not be a circle, maybe a square, it may be some other shape. But if we can, then what do we have? We can approximate the volume by taking the area of this sort of thin disk, if you will, and multiply it times its thickness. What's the thickness again? That's the delta y here, right? That's the thickness here. So this again is the delta y here. Thickness there. And so the volume of this piece we can approximate as a right cylinder. In other words, its area, cross-section area is A, and it's as a function of y, and the thickness is delta y. Okay, and I can actually do the area as a function of y sub I. So in other words, I can actually come across here and get that actual area for that slice right at that piece times delta y. Now it's not exactly equal to the volume of this slice because these sides are changing, right? They're curved, so the area changes as we slightly as we move up. But approximately, we could pick some arbitrary y sub I, pull out that circle, and use that area of that circle, or again, whatever shape it is. Again, I keep saying circle, but it could be something else. Whatever shape it is, as long as we can find that area. So we approximate the volume as the area times the thickness, right? That will give us cubic units for the volume. And so that's for that one slice, and we have n of these slices. So to find the volume, we add them all up, I equal 1 to n. All right, we find all these slices that we're finding the volumes for, and we're going to add them all up, and there's our approximation for the volume of the whole thing. It's an approximation again because we're assuming constant cross-section here when in fact there is some change, right? It's not really constant. So how do we get a better estimate? Well, we let n get bigger and bigger. We have delta y get smaller, more and more subintervals, right? Delta y gets thinner, but we continue to approximate that volume in this case. And so what can we do then? We can push that value of n to infinity. Take the limit as n goes to infinity of that. And what do we have here? Notice this is a Riemann sum. Taking the limit of n goes to infinity is going to give us a definite integral. Notice we're doing it with respect to y, and y is going from what? From 0 up to h. And the function a sub y, and notice it's dy, right? That's the variable of integration. So if we can find the cross-sectional area of an arbitrary at height y, if we can find that cross-section area as a function of y, then we'll be able to find the volume of the solid body. So, or this, in this case, this dome-shaped object, whatever it is. So let's take a look at an example that's a little more concrete than this, but this is the idea. And it actually gives us a definition now right from this, that if S is the solid body that lies between y equal a and y equal b, in general we did between y equals 0 and h in our example, if the cross-sectional area S in the plane p sub y, so what we mean is at some arbitrary height y, if we cut across a plane intersects our solid body and we take a look at that cross-section, if we can define that area, that area at that height y to be a of y, and if a is a continuous function, which it should be for the situations we're looking at, then the volume of that solid body is given by this integral, which is exactly what we just derived. So let's take a look at an example then of this, and we'll find the volume of a right circular cone of height 10 inches whose base radius is 5 inches. Now, some of you might know there is actually a formula for a right circular cone, but we're going to derive this. So a cone, right, looks something like this, like an ice cream cone, and except I'm going to make it to be an inverted ice cream cone, so the point's at the top just for ease of calculating this thing, and so calculating the volume of this. So what I'm going to do again is I'm going to set up my x-axis here, and I'm going to do my y-axis along here. So I'm going to let this be y equal 0, and then at the top of the cone, all right, that's y equal what? What's the height of this cone? 10 inches. So that's, we'll just say 10, but it's in inches, right? That's the top. So we're going to integrate from 0 to 10 inches. And what we need to do is find this area at an arbitrary height y. Right, the area that a plane, right, intersecting this solid body, what is the area of that intersection? So I'm going to come up here to an arbitrary height y, and look at the intersection here. I'm going to take out a little tiny, and obviously this time we are going to have a circle, right? If I slice through there, if I pull that out, what do I have? I have a circle, and the radius, we'll just call that r for that little circle. And obviously as y moves up and down, that circle is getting bigger or smaller, right? This is at the bottom it's big, and at the top it's small. And so what's the area of this? It is equal to pi times r squared. So I need to figure out what r is as a function of y. So how can I do that? Well, I'm going to look at another intersection of another plane. This was a horizontal plane. Now I'm going to come across with a vertical plane that will cut this cone vertically. And what will we see? We will see a triangle, won't we? And again, let's put this again would be again the x-axis, and here's our y-axis. Okay, and what do we know about this? We know that the height of this thing is 10 inches, right? And also we know that the base radius is 5 inches, so that's going to be important here. The base radius, so we got a circle. If I drop the line perpendicular from the top and it hits the center of that circle, then this right here to here, that's our radius of 5 inches. Okay, and so remember we came up here to some arbitrary height y, and right here then this is our slice right here that I've drawn here and pulled out, looking from the side. This is from the side, and so this length here would be the diameter. What we're looking for is R. Notice that R is this length here. That's R. That little half length right there is the value of R. So, is there a way to relate R to Y in this diagram? And the answer is yes, and that is by similar triangles. Right? Similar shapes. What do we have with similar shapes? We have side lengths are in proportion to one another. Similar shapes are just scaled versions of one another. Okay, so for instance, I see two similar triangles here, and let me show you one of them. It's this big triangle here. I'm going to sort of draw it here, dropping down. That's a 90-degree angle over to here, and then we have this side. It's actually a right triangle, isn't it? It's got this side length is 5. What's this length here? What's the same as 10? And then we got the hypotenuse. We can actually find the length of the hypotenuse if we wanted to. Okay, so that triangle, and then I'm going to show you the other triangle. I'll try and do this in purple. It's right here, outlining it. This triangle, this is also a 90-degree angle, and this triangle here, notice, is similar to the bigger one. Why? Because they have this and this are both 90-degree angles, and they share this angle at top, and of course this angle and this angle have to be the same as well. And so the angles are the same, but the side lengths are not the same, right? This is 5 and this is less than 5, and this is 10 and this is less than 10, but the side lengths are in proportional to one another. So this side length here, R, corresponds to the side length here, 5. This side length, right, corresponds to the big side length of 10. The question is, what is this length? What is this from here to here? Well, can you figure that out from the diagram? What this length will be? This is 10. This is Y. So what do we have left over? 10 minus Y. That's what this length is. And it makes sense again, right? If Y is 0, then we're talking about the entire big triangle, which is has a height of 10. If Y is, say, 5, then what's left over up here? 10 minus 5 is 5, right? If Y is 6, 10 minus 6 is 4, and so on. So from this, we have that side lengths are in proportion to one another. So side length R in the small triangle is to its other side length, 10 minus Y, which we just found, as what? This proportion is the same as the proportion of the bigger triangle, which is 5, right, this side length, to this side length, which is 10. By the way, 5/10 is just 1/2. Right? So this is important. So side lengths are in proportion. So now I can take this equation, cross multiply. 2 times R is 2R. 10 minus Y times 1 is 10 minus Y. And now I can solve for R by multiplying both sides by 1/2. Okay. And there I have it, R as a function of Y. Now make sure this works, okay? We know that if Y goes to 0, that R becomes 5, doesn't it? Right? If Y goes to 0, we're talking about R is 5. Is that true in this formula if Y is 0? Yeah, I get 10 minus 0 is 10, 1/2 of 10 is 5. And then also as Y goes to 10, what's happening to R? R is getting smaller, 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 smaller. By the time Y gets to 10, R has gone to 0. Is that true when Y is 10? Is R equal to 0? Yes. So notice a quick check of that to make sure that your relationship is indeed accurate. So if I take that now and bring it back up here, then R is 1/2 times 10 minus Y. I can plug in and I get the area as a function of Y equal to pi times R squared. R is 1/2 10 minus Y quantity squared. And so I can clean this up. 1/2 squared is 1/4, so this is 1/4 of pi, or pi fourths, 10 minus y quantity squared. And I'm going to leave that squared. You could expand that out, but I'm going to leave it like that. So that, first of all, is step one, finding the cross-sectional area. Now, it's not constant, it's changing, and we can see, right, notice when y is 0, we're going to get the area of the base, right? And the base had a radius of 5, and notice when I plug in y equals 0, I get 5 squared, right? And then and so we get the area of this circle at the bottom, right, when y is 0. Sorry, I said that wrong. Y is 0. We get 10 squared. So why would pi fourths times 10 squared be the area of a circle of radius 5? Well, we do a little manipulation and see that that's exactly the same thing, because the 1/4 can will come in and distribute. You could distribute that inside here if you think of 1/4 being 1/2 squared. So I can bring it in as a 1/2, and 10 halves is 5. So trust me, if y is 0, you'll get the area of this circle down here. You can compute pi times r squared. It's equal to this if y is 0. And obviously if y is 10, the area of the circle goes to 0, which is clear from that formula. Okay, so now what do we do to find this? We're going to integrate this cross-sectional area from what? Well, what are we integrating from? Y equals 0 to y equal 10. And that's the volume. So the volume is the integral from 0 to 10 of pi over 4, 10 minus y squared dy. And now we just have to evaluate this integral. I'm going to go ahead, and you could expand this out and just do it that way. I'm going to do a little substitution. I'm going to let u equal 10 minus y, so that du is what? Derivative of 10 minus y is -1. So du is negative dy. I've got just a positive dy, and so I'm going to multiply both sides by -1 here. And this then gives me what? The pi over 4 I'm going to pull out. Go ahead and pull that out. Constant multiple. I also have to change my limits, don't I? Notice my limits in this are going to change. This is a change of variables, right? So I have to change the limits as well. This relationship, if y is 0, then u is 10 minus 0 equals 10. And if y is 10, then u is 10 minus 10 equals 0. So they kind of flip-flop, right? So this becomes the integral from 10 to 0. And 10 minus y is u squared. And the dy is negative du. So I'm going to pull that negative sign out here, du. Okay, so there I've done that substitution. I can also, if you, you can integrate it if you are uncomfortable with this. Notice negative this integral from 10 to 0 is the same as what? Positive this integral from what? If I change the sign, what happens to the limits? They change, right? So I could just go back and do that. And now I can find the antiderivative of u squared, which is 1/3 u cubed. And I'm evaluating that at 10 and at 0. And so I get pi over 4, or actually 3 times 4, pi over 12. Well, let's just do it this way. 1/3 10 cubed. And at 0 minus 0, obviously. And so I get 10 cubed is 10 times 10 is 1,000, right? And 1,000 divided by 4 is 250. So this simplifies down to 250 pi over 3. And that's the volume. What are the units, by the way? Because our units were inches for the height and the radius. Remember, volume is in cubic units, so this is cubic inches. Cubic inches. Okay, but that's how we can find the volume of a cone where the cross section is changing. It is not constant. So the bottom line is, for any shape we have here, the trick is to find this cross-sectional area as a function of the height. I'm doing it with respect to y. If you want to lay this thing down on the side like this and integrate with respect to x, you can do it that way as well. Okay, I like to have my things just set them on their base and then integrate upward. Typically is the way that we want to do it, but we can modify that if need be. Okay, so we'll stop here, and you can see these problems take a little bit more thought in setting up. The next one we're going to look at, in the next video, we'll look at the volume of a sphere. We're going to find the volume of a sphere. Okay, that'll be next.